Hey, I'm Tyler. I go by AtHeartEngineer on the internet, and this is Ying Tong. So I'm an engineer, she's a cryptographer, so we're gonna kind of go back and forth between the mathematical view and then like the layman's explanations for a lot of introductory cryptography. So cryptography really is kind of a blend of art and science, and it's the art and science of secrets. All right, yep, this one's you.
Yeah, and oftentimes we think of the purpose of a cryptographic system in terms of these three properties, CIA. So firstly, confidentiality, the property of keeping your messages secret and ensuring that they're only ever read by their intended recipient. Integrity, being assured that the message at the time of reading has not been tampered with from the time of sending. And authenticity, that the message was indeed sent by the expected sender and not forged by someone else. So a cryptographic system should provide assurance of these three properties.
So this really comes down to you basically have these puzzles that are very easy to solve if you have the right key and very hard to solve if you don't have the key. There's a little note at the bottom. There's a lot of nuance here. This is very hand wavy. You're gonna hang out on this side? Okay. But yeah, so easy to solve with a key. If you don't have the key, very, very hard. So the topics we're going to go over are hashing, encryption, signing, and what we're now calling programmable cryptography, which is ZK, MPC, and FHE.
And you can kind of think of this breakdown as corresponding to the three properties that we discussed just now. So hashing is a primitive that's often used to provide integrity, assurances of integrity. Encryption helps us to preserve confidentiality, and signing is a way to provide authenticity. And these three former primitives and protocols are what we consider first-generation cryptography in the sense that they're purpose-built for a specific protocol. In the rest of Devcon, on the applied cryptography track, you're going to hear a lot more about programmable cryptography, which usually involve more heavyweight and more general purpose protocols.
All right, so hashing is a one-way function that basically gives you a fingerprint of some data. You can think of this as just this magic machine that you put data in one side and then that fingerprint comes out the other side. So this is an example of what that machine looks like, which is pretty gnarly, but essentially it comes down to you put in, for example, a password, it gets hashed, and then some fingerprint comes out the other side. Yeah. A good analogy for this is like blending fruits in a blender, right? Like you can't get the fruits back out, but you have a consistent like color, right? If you add just bananas in, you're gonna get the same color basically every time. So unique input, unique output. These are always fixed length. So that's to stop certain types of attacks where you can try to like infer what kind of data went in. And you can see, so hi, hell, help, and hello, like they have very similar letters, but they're totally different fingerprints. You want to talk about this?
Yeah, so we've put in sort of snippets of the relevant Devcon talks throughout our slides to help you orient. And actually, this talk already happened, but it was an example of how you can build a general purpose proof system just using a hash function as a primitive. So you can go back and watch this talk. You can do a lot with hash functions.
Cool. So a common reason that hash functions are used is passwords. But as you can see, if two users have the same password, they have the same password hash, right? So This allows an attack called a rainbow table attack. Basically, you just hash all common passwords, and then now you have this known fingerprint, and you can use that to attack people's passwords. But there's this thing called assault you can add, which is essentially just tacking a random string that's specific to each user to the end of the password and then hashing it. Now you have a unique fingerprint for every password hash. So this is just like a example of how hashing is used very commonly. So pretty much every popular website that has logins uses bcrypt with per user salts. Like this is a pretty common technique. All right, this is all you.
Yeah, and I think hash functions are a great introduction as a cryptographic primitive because they seem very simple. The API is really straightforward, but a cryptographic hash function actually has to fulfill a few properties. So we won't go over them in detail, but I think I put this in to highlight also that there exist non-cryptographic hash functions, so that are way more efficient than cryptographic hash functions, and that are suitable for use cases such as hash tables, which are not sort of high security. So in hash tables, for instance, we don't need the collision resistance property. In fact, in hash tables, we have many techniques to handle collisions, buckets. And at the same time, cryptographic security of a hash function is, I think, literally defined as for how long has this hash function remained unbroken for. And that's where the art of cryptography comes in, cryptanalysis, security analysis, and reasoning about the cryptographic security of a certain primitive. So yeah, hash functions we chose as an introductory primitive, just to give you a taste of what they can be used for, how we reason about them. Yeah, another very common use case is in Merkle trees. I'm sure we're all familiar. It's used in Git to produce unique digests of a repository. It's used in blockchains to produce cryptographically linked headers from block to block, for instance, in the Ethereum state. Yeah.
All right, so now we're going to go over encryption real quick. So one of the original encryption algorithms that were used is called a Caesar cipher, and it's terrible. But basically, you take the alphabet and you shift it by some number, and let's say if we want to write hello, you're going to identify those letters and then basically just translate to the new code, right? And if you want to reverse it, you basically just shift it the other way, and then you get the original message back out. This is 4.6 bits of security, so basically 26 letters minus 1, and it's terrible. We have much better techniques nowadays. So symmetric key encryption, which is basically what a Caesar cipher is, a type of symmetric key encryption. But it's when all the parties that are participating have the same key, right? So use the same key to encrypt and decrypt. There's no authentication, so you don't know who encrypted the message, and basically anyone with a key can decrypt it, but it is fast, and it's used very commonly with data at rest or TLS, stuff like that, stuff where you need high bandwidth. Common examples, AES for an actual algorithm that's used. Oh. All right, so yeah, secret key, plain text to go in, you get some ciphertext out. To decrypt, you put in a secret key in your ciphertext, you have a decrypt function, and then you get your plain text back out. All right.
Yeah, and yeah, so symmetric encryption is suitable for when both parties are able to establish a common shared secret and to use it both to encrypt and to decrypt. But in many use cases, we want the ability to, say, asynchronously and non-interactively encrypt a message to a recipient. And in this case, asymmetric encryption comes in really handy because all you need to know is the public key of your recipient, and they can decrypt the message at any time they want without your help. So we put the API here. I think what's important to note that's different from symmetric encryption is that the encryption and decryption keys are different. And in particular, when we encrypt, we don't need any privileged information. And when we decrypt, we need a private key that should absolutely stay secret. So a very closely related primitive in public key cryptography is signatures. And you can think of a signature as a sort of watermark. So the API here changes slightly. In this case, we're using a private key to sign a message and using the public key to verify that it was indeed signed by who we expected. So it's really interesting. For example, like the same crypto system RSA can be used for both encryption and signing, and oftentimes, and it just involves flipping actually which key you use. So I think something to note here is that let's say in RSA to verify a signature, you actually decrypt it using one of the RSA key pairs, and this means that anyone can read the signed message. So it does not give you the same properties of confidentiality, but it does give you authenticity. And you can look out for, this talk already ended, but in Ethereum, they're currently using a signature scheme that is not post-quantum secure, and they're actively thinking about how to transition to post-quantum.
Yep. So a common paradigm in like email, for example, is used use signing and encryption, right? So you want to be able to prove that you're the one that created the message, and you only want the recipient to be able to read it. So in order to do this, you would put in your private key in a message, you would sign the message, and you would take that signed message, take the other party's public key, and encrypt the message, and then send it to them. So they can take that, decrypt it, and then also verify that you are the sender. All right, so HTTPS, everyone knows what this is. It's a little green lock. Make sure you have a secure connection to the server. This is a little hand wavy, but the general explanation is if you connect to a server, you do this key exchange. It's called Diffie-Hellman, which I'll go into in the next slide, and you get out a symmetric key, right? So public key cryptography is slow compared to symmetric key. So yeah, basically to make web pages load faster, you would do this Diffie-Hellman key exchange and then get out a symmetric key that only you and the server know, and then from there on you can do faster messages. So the way this works is you start with some shared paint, right? Some shared colors, and this is the paint analogy for Diffie-Hellman. But you start with some shared paint, and then you each have some secret color, and you combine those to create these two inputs. You exchange the inputs, you add back in your secrets, and then you end up with the same paint color on either side, but no one in the middle could know what your secrets are.
Yeah, so we went through hashing, encryption, and signatures. And we're considering these to be sort of generation 1 purpose-built cryptography that are really lightweight and just do their task really well. What's been emerging and what you'll see a lot of at Devcon is programmable cryptography. So These include zero-knowledge proofs, multi-party computation, and fully homomorphic encryption. And these protocols are a lot more heavyweight in the sense that they involve, usually, lots more assumptions, security assumptions. But on the other hand, they're a lot more general purpose in the sense that the end user is free to define any arbitrary relation. They're not limited to, say, signatures, encryption. And in that sense, this class of primitives are programmable. Yeah, I think these talks happened already. But introductions to this paradigm of programmable cryptography. So we'll quickly go through the three categories. Maybe the most popular one is zero knowledge.
Yeah, that's great. So essentially, zero knowledge, ZK, is a way for a prover to prove some statement to somebody else and they can verify it. So for example, you could have your picture and then some private data, your age, your date of birth or whatever, go into some CKP, and then out comes a hash of your photo and then basically a thumbs up that you're like over 21 or whatever. So you need that hash of your photo to make sure that someone can actually authenticate that it's you. They can see the image, make sure that it corresponds with your age, and yeah, you can prove you're over 21 without showing your license or your passport or whatever.
Yeah, so the over 21 relation is just one example of a relation that you can prove in zero knowledge. The point here being that this is an arbitrary user-defined relation. And as Tyler said, the prover can keep their secret witness unknown to the verifier and yet still convince the verifier that it satisfies the relation and corresponds to a certain agreed upon and publicly known output. So another interesting property of many zero-knowledge proof systems is succinctness. And what this means is that the prover's communication is much smaller than the size of the relation that he proved. And this comes in handy in ZK rollups, which I think many of us have heard about, whereby we outsource very heavy computation to some well-resourced machine, off-chain, and then simply submit a very small proof of its validity on-chain. The point here being that verifying the computation is a lot cheaper, and we don't have to pay that much gas for it. There's also many other sort of developments in zero-knowledge proof systems. So I think Yusuf actually will talk about elliptic curves and snarks right after us. And many more exciting examples of applications that use ZK. I think Privado right before us, for example. So now, if we sort of, if we introduce this setting where the witness is no longer held by a single party, namely the prover, and we move to consider like multiple parties working together to compute a relation, this would bring us into MPC, multi-party computation. And this is a superset of zero knowledge. So it is a way for multiple parties to jointly compute a function over secret inputs. So yeah, I put this visual here to show that, well, once again, we have an arbitrary function, but what's changed is that the witness, the secret input, is now split across multiple parties. And we can actually combine multi-party computation with zero-knowledge proofs and get publicly auditable MPC. So we can have both an MPC and a succinct certificate that the MPC was done correctly. And you can, yeah, we actually have a bunch of MPC talks at this conference. So yeah, this ZK MPC is what I was talking about, publicly auditable MPC.
Yeah, so this is a project that our colleague Andrew wrote. So it's a game where you can play a modified version of rock, paper, scissors over MPC. So only you and the person you're playing with are like actually participating. There's no like intermediate party, and you can trust that each other aren't cheating. So fun game.
Yeah, and these are some other applications of MPC that you can hear about. So the final sort of, I think the most heavyweight primitive in programmable cryptography is fully homomorphic encryption. And the API of this looks pretty different. So in this case, the holder of the secret data encrypts it homomorphically. So it transforms it into this sort of ciphertext that preserves the privacy of the data, but also preserves the structure of it such that any party can transform it according to any arbitrary function. So once again, this is fully programmable, but all the work is kind of outsourced to this arbitrary third party. So this third party performs an arbitrary computation and then returns. So this third party is working completely blindly and ends up only with a ciphertext form of the output. And the point here is that only the holder of the secret key is able to decrypt the output to some sensible plaintext. And yeah, there's actually been a bunch of cool experiments using FHE by Cursive. So you can check that out. No, yeah, that's already over as well. So yeah, I think that's all we have. And do we have time for questions?
Questions?
Thank you. First, maybe give a round of applause to the speakers for a very nice overview of cryptography. So it's a little bit over time, so we have maybe time for one question, but I think one that came in very early and was upvoted a lot very quickly was, what are some good resources to dive deeper into formal cryptography as someone with no prior experience?
So there is a elliptic curve cryptography primer by Cloudflare that I would recommend. It's a little long, but it's very understandable. Like you can get through that pretty well. 3 Blue 1 Brown did a video on how Bitcoin works that he dives deep, and it's like 20 minutes, and he goes over hashing and signing pretty deeply. And yeah, I mean, I think those are probably 2 good options.
Oh, also, there's this legendary cryptographer, Dan Bonnet, who's done a bunch of open courseware courses with like videos and course materials. I think it's on Coursera, actually. So I highly, highly recommend that one.
Cool, and maybe watching back the talks that you linked as well. So watching the videos back. Very nice. So I think we're at time. We have a few minutes to switch over for the next session. But yeah, we'd like to thank the speakers again, and we see you soon. So we'll be back in 4 minutes, but I was just advised to say there's quite a lot of cans and stuff left around.